Okay, good afternoon, everyone. I know it's been a long 3 days. Unfortunately, I've only been able to join today, but thank you very much for everyone who's stayed till our final session today. Over the next couple of hours, we want to provide you an overview of our circular chemistry center. We've already had a showcase earlier this year, so this is really a summary of some of the work that was presented in March for the first hour, and then for the second hour we've got 3 of our early career presenters presenting. My name is John Wagner. I'm from Loughborough University. I'm the program lead for the center. Unfortunately, Jin, who's the PI of the center, has commitments today, so he couldn't join, but some of you might have met him on Tuesday of this week. So I don't think I need to present that. Of course, we're one of the 5 centers which is funded through the NICER program. And first of all, why are we interested in the chemical industry? So we believe the chemical industry is very important. Together with pharmaceuticals, it's the UK's largest export sector. It has an annual turnover of around 32 billion. And the demand in chemicals is expected to double over the next 10 years. But despite that, most of the chemicals at the moment are based on fossil resource inputs. And as we're reducing the use of fossil resources for transport and we're increasing our chemical consumption, chemicals are expected to account for around half of all fossil fuel consumption by 2050. It becomes increasingly important to find alternative feedstocks and become more circular. On top of that, it's a very energy and carbon-heavy industry, so it's the second largest industrial CO2 emitter for the UK. And a lot of the chemical products that we produce, at the end of use, we dispose of them, and they can end up in landfill. And depending on the calculations, we've only got around until the end of a decade in landfill capacity available. So becoming more circular is a very important issue for this industry. So the vision of our centre is to then transform the chemical industry from its linear model towards a more circular model. Chemical industries is a very complex sector. There's thousands of different chemicals. So when we set up the centre, we decided to narrow it down to organic chemicals, so carbon-based chemicals, and specifically within that olefin-based chemicals, which account for about 70% of all organic chemical productions. The centre is led by Jin Chuan, who started in Loughborough but has recently moved to Surrey University. And we've got 7 other partner institutions: Loughborough, Cardiff, Liverpool, Hertford, Sheffield, Newcastle, and Imperial College. And we started with around 23 partners, but now we're working or engaging with over 100 different organizations. So let's start to look a bit of a background about chemical resources flows. So generally we take our fossil material input. We can then refine this input into platform chemicals. Those platform chemicals are further converted into our desired chemical products. They are converted, then sent to the consumer, they're used. And at the end of the use, we might produce solid wastes, which if we're lucky, we can separate them, source segregate them, collect them, and recycle them. So there's a couple of important things to consider here. So for circular economy, for chemicals, they're based on carbon. So really, we're not talking about decarbonizing the chemical sector, but we're talking about reducing that fossil input. So we want to defossilize the center. So what we want to achieve is really retaining the carbon within the chemical sector and circularizing it. So as I said from a previous slide, we can collect that chemicals like plastics at the end of the use. But if we look at all plastic production, only 9% of polymers that have ever been produced have been recovered so far. One of the issues is the source segregation, but the other issue is that only about 40 to 50% of polymers can actually physically be recycled. So we've got a huge amount of solid chemical waste that we still need to deal with. And this is the other issues was mixing contaminated waste. So we've got plastics used for the food containers. We might have food residues. So one potential solution is that we try and improve the separation so we can increase the recycling. But even if we have a perfect recycling system, we still have a lot of waste remaining. So at the moment, this might either go into landfill or we send it to incineration or energy from waste. And of course, this incineration then releases CO2, which is one of our waste products. Now, this is just focusing on the solid fractions that we can actually separate, but a lot of the chemical materials are actually not solids, but they're things called polymers in liquid formulation, stuff like paints, coatings, shampoos, conditioners, paint, sealants, and things used in agriculture, water treatment, which have a huge global market. And there's a big review going on by the Royal Society of Chemistry looking at these chemicals at the moment. But unlike the solids, it's quite difficult to collect these materials. So they might go into your drain, into your ecosystems, or they're directly released as CO2. So it is obvious that we need to find a different way of meeting those carbon shortfalls for those chemicals that we can't collect. So where we're going to get the carbon from to meet that gap. Two of the solutions could be that we use the CO2 that's released in the environment, we electrochemically reduce it back into chemicals, or we could use biomass and convert biomass, which uses the CO2 for growth, and convert it into chemicals. And one of the big advantages of that is that it also gives us a potential to make the chemical industry carbon negative. So if we capture that CO2 and convert it into material, we store that carbon, and we move from a fossil-based system to a carbon negative system. And the final consideration is that the chemical industry is actually very closely linked to energy system as well. So when we take the fossil fuels out of the carbon, we don't distinguish whether this is a chemical feedstock or a fuel. In fact, we measure all this material in terms of energy units, and only when it comes out of a refinery, we start to say, okay, this is the quantity of chemicals that it's got. And a lot of the processes that we use in here are also very energy intensive. So we need to think about where do we get the energy from. If we look at UK energy consumption patterns, we can see that we've got different demand patterns, and also our availability of renewable energies is very fluctuating. So using the chemical sector could be a big opportunity to use the energy when it's in excess demand, use it in the chemical products to store it, and help us balance the grid. So just to summarize then for what we are trying to do, so we've got our linear economy starting from oil and gas. We produce our petrochemicals, intermediates, we produce polymers, but also other chemicals into our finished products. And then it moves into the use phase, where at the end of that we produce waste, and this waste is currently collected, sorted, and then disposed. So we have already done quite a good job in the UK focusing on mechanical recycling. So UK plastic recycling stands at around 45%. But as I explained, that is only a small fraction of all the chemicals that are used. So the next thing we can look at is use that material and then break it down into its chemical building blocks through chemical recycling. But even so, we will still have a lot of emissions in the form of CO2, and then we can start to look at electrochemical reduction, electrochemical recycling, using this excess renewable energy. Or finally, that CO2 is released, it is captured in the form of biomass, and then we can use this biomass and convert it back into fresh chemical feedstock. And this is really what our center was based on. So this is the same kind of diagram with a little bit more detail. And I'm going to now explain more about the center structure and what we're trying to achieve in the different work packages. So our center consists of three integrated themes. The first theme is focusing on underlying technologies that we need to achieve this transition. So how do we take the waste and convert it back into new feedstock? How do we use the CO2 that's released and reduce it into chemicals? Or how do we use biomass to meet our technology gap? So this is really focused on lab-based research to develop new technology options to supplement the technologies that already exist. Theme 2 then looks at the application of these technologies. How can they be used as part of a wider system? So, for example, we might be wanting to produce a certain product, and then we can see how do we produce it currently, what are the new ways of producing that, and then we can compare the economics, but also the environmental impact, and find the social impacts of different system routes. The final theme is looking at anything that is non-technical, so all the kind of barriers and opportunities associated with the circular transition of the chemical industry. This ranges from the finance, how do we pay for this, or who should be paying for that? How do we work with society, and what do they want from a transition? Engagement with industry, of course, is very important, the ones that are going to enable this. And finally, working with the policymakers to understand how do we create the favorable frameworks that encourage further innovation. And then all these different areas of the center are linked together through case studies and cross-theme integrations. And I will present some example of them as part of theme 3. Now, theme 3, as I said, it's based on the enabling technologies. And there's already some technologies out there, but really we are very conscious that we need to create more research. And in the center we selected 3 different areas of development. The first one is the electrochemical reduction of CO2. One is the biothermal, the thermochemical conversion of biomass and waste. And the third one was the more selective depolymerization of plastic waste into chemical building blocks. But of course, these are just 3 solutions. There's many different solutions out there, and of course we can't do all of them during the center, but we thought these are representing the different technologies that will be required to enable this change. So the first work package, which is co-led by Liverpool University and Loughborough, is a focus on the electrochemical reduction of CO2. And as we can see, carbon is a fundamental part of many different materials, including the polymers, chemicals, and materials sector where our center interfaces with. So there's a big opportunity to capture this carbon and then store it or lock it in our chemical supply chain. To do that, we can either use direct air capture, where we remove CO2 from air, or we can use a point carbon source, and then we combine it with renewable electricity in an electrochemical cell to reduce the CO2 at the cathode and produce oxygen at the anode. In the center, we took 2 different approaches. The first one is we can reduce the carbon dioxide into carbon monoxide and hydrogen for use as syngas. And there's already many different chemical routes available to then convert this syngas into different chemicals. And the nice thing about this approach is it's relatively straightforward. We can see we only transfer 2 electrodes on the reduction side and 4 on the oxidation side. So it's a reasonably well-developed technology. But of course, what we would really want to do is produce olefins directly, so where we reduce CO2 into higher hydrocarbons like ethylene, propylene, etc. But then we can see that the chemistry here is a lot more complicated, so we need to transfer a minimum of 12 electrodes. So we need much more advanced catalysts which enable us to do that. The other difficulty with reducing CO2 is that we now need to develop a three-phase system. So we've got our solid electrodes, we've got our liquid electrolyte in the center, and we've got our gaseous carbon dioxide feed. So we need to overcome those mass transfer limitations. How do we transport the CO2 to the electrode surface? So conventionally, you would take your fuel cell. You've got your electrolyte in the middle, and you bubble the CO2 through the electrolyte to come to the electrodes. But our team in Loughborough developed a new system where the CO2 is brought into the cell from the outside. We've got a permeable membrane, so it basically comes from the back to the electrode surface where it can then be reduced. So I'm not going to go into the detail, but really, how do we develop this technology? We need to think about developing new catalysts. So for example, when we want to convert CO2 to syngas, we want to have high selectivity to our carbon monoxide. And what we've got different electrode materials like copper oxide and tin oxide, and we can see that they provide us with the differences in our product distributions. But now what we can do, we can try and bring them together to then tune our product selectivities. So here we have pure copper oxide, and then we dope different amounts of tin onto the surface, and we can see that at a certain loading, we massively increase our selectivity to carbon monoxide, which increases the efficiency of the cell. And at the same time, we can see that the electron current density, which is negative, massively increases at the bottom. So this cell now is able to reduce a lot more CO2 per unit surface area, making it more efficient. One of the challenges still with these systems is the longer-term stability. So they have a very high performance at low times, but we can see that over time our current density reduces. Our selectivity or the desired product reduces. So the next challenge is really how do we understand what is causing this instability. Part of that is to do with flooding of a cell where the gas is meant to come in from the outside, but actually the liquid is now penetrating through the electrode. And this is one of the challenges that we are working on for the remainder of the center. A similar approach is taken for the reduction of CO2 directly into higher hydrocarbon products. So in this case, again, we've got two different electrode materials. So metals like silver, gold, or zinc are good at catalyzing that initial CO2 reduction step, whereas copper is very active for then catalyzing a dimerization step into higher hydrocarbons. So again, we can try to combine those two materials together by loading different amounts of silver onto the copper surface, and then understanding how this affects our product selectivity. And again, we can see that after a certain time, now more than 50% of those products are in the higher hydrocarbon range. The second work packages is focused on the direct on the conversion of either waste chemicals or waste biomass, or sometimes mixtures of those two materials. So you might have your plastic container and it's contaminated with food waste or mixed municipal waste. And there's many different options available for us for converting biomass. So we can have a simple mechanical process where we're just drying it or pressing it, things like producing vegetable oil. We can use biological processes like fermentation, algae-based technologies. We can use chemical technologies, or we can use thermochemical processes where we're using high temperatures and sometimes high pressures to break down our material into oily-based products. And the advantage of these thermochemical processes is that they can deal with a much higher variety of material to try and produce a more uniform material, similar to the kind of fossil process that produce fossil fuels, and then we feed that through a refinery. In our group, where we're looking at a hydrothermal process, so you can use dry biomass, that would be pyrolysis, but we are specifically focusing on wet biomass, where we don't want to dry the biomass before use, and instead we actually conduct a reaction in water. So effectively, we've got our biomass, our chemical feed. We add water, and then we put it in the reactor, which acts as a pressure cooker, so we keep the reaction in liquid phase, and we can see we can go up to temperatures of around 370 degrees if we increase the pressure high enough. And the big advantage is we don't need to evaporate water. It's much more energy efficient, and water actually helps us to break down those chemical compounds more effectively. And then out of the reactor we get a range of different products. The one that we're particularly interested in is the bio-oil phase, and converting that back into more chemicals. But we also produce an aqueous phase, a kind of solid product, and some gas. And one of the challenges is, how do we not just use one of these product phases, but what do we do with this aqueous phase? If we can't use that, we can't simply discharge it, and that would inhibit the use of this process. So the first project that we looked at was the conversion of a distillery residue, called draft. So it's quite a nice, well-defined material. It's got a carbon content of around 50%, but we can see, like most biomass, it's also got a very high oxygen content, and because of that, its energy density is quite low. So here the energy density is around 22 megajoule per kilogram, compared to diesel or petrol, which is in the range of 35 to 40. So what we want to do is concentrate as much of the carbon into the oil phase, but remove some of its undesired other elements like oxygen and nitrogen. So the first thing, we can put it into our reaction at a loading of around 10%. We can look at the impact of temperature, and we can see, well, we get oil yields of around 30-40%, but we do see much higher carbon recovery of up to 50-60%, which means that we can see this concentration of carbon into our oil phase. But of course, we only recover 55% of the carbon, so only 55% of the energy is now recovered into the oil phase. So what we wanted to do then is try and see, can we develop catalysts which allow us to increase the carbon retention into the oil phase and make the process more efficient. But one of the problems with the use of catalysts in the system is that we produce all these different product phases, particularly the solid product, and how do we, if we use the expensive catalyst and it's mixed with our ash phase afterwards, how do we separate this material afterwards? So a lot of work in the past has been used on the use of noble metals, but not really on how do we separate the catalyst and reuse it going forward. So we thought, what if we could use a magnetic material, which you can then separate from the solids using electromagnet. So we looked at both iron oxide and nickel oxide catalysts, and we supported them onto a carbon support, and then we added them to the reaction. And as we can see here from the carbon distribution, now we could see by using both iron and nickel, we managed to significantly increase the carbon retention in the bio-oil. So we went from about 55% to over 80%, which is one of the highest carbon retentions that has been seen in the literature so far. But not only did we increase the carbon retention, but we also improved the quality of this oil. So now we can see that without catalyst, we've got a carbon content of around 68%, but with our iron oxide catalyst, we managed to increase this to over 80%. So these catalysts are quite promising in increasing our carbon recovery. And at the same time, iron is quite a cheap material to use. But still, we want to understand then, can we actually use this magnetic separation? It is a little bit more complex, and we produce some very sticky materials, so we had to develop a procedure to then separate the oil from, the solid from the catalyst, but then in the end we managed to use this magnetic technique and recycle our catalyst for up to 5 cycles with a pretty good retention of its catalytic activity. Now, the last project used a pretty nice and clean biomass feedstock, which is really what we want to work with. But actually, a lot of the chemical wastes are mixed with other materials. So here we had a project where we took waste residues from a local waste management company, and in our area in Loughborough, waste is not very well separated, so we throw the food waste and organic waste all together in the same black bin waste. So they currently use a wet mechanical process to separate this into a set of stages to recover metals and other valuable materials. In the end, they produce a liquid slurry which they feed into an anaerobic digester. But at the moment, we produce 2 key waste products. The first one is a dry material called flock. It consists of paper and plastics. And the other process produces very fibrous residues, which is a wet, horrible kind of material. And they have no use for these, so they're disposed to via landfills. So they thought, what if we try to use our hydrothermal process to convert these into a more useful product? One of the big problems with using waste materials, we can see they're very heterogeneous materials, but they've already gone through a lot of processing, so it's no longer possible to separate them into their individual components. So if I want to do a study in Loughborough and I want to compare that to another study in another place using a different waste process, or even if I just take samples of waste in summer to winter, the composition is very different, so it's very difficult to compare these different materials. So one of the key challenges was then how do we characterize this waste in a way that we can then compare different waste materials very well to each other. So we could use chemical spectroscopy. So here we used HEIR analysis to look at the 2 waste samples, and we can compare them with known model compounds. And that told us, okay, yes, we've got some PET, we've got some polyolefins in there, but we've also got cellulose, probably from a paper waste, and maybe some lignin from other biomass wastes. And this is useful. It tells us what we already know, but it doesn't tell us what are the relative quantities of these different materials. So we spend quite a lot of time using different techniques to further characterize materials. So here you used thermogravimetric analysis, where we look at the thermal decomposition profile of a waste. We looked at the hydrolysis of the materials to look at the cellulose and the sugar content. And based on that, we then were able to create a picture of what are the key components of these waste materials. These might not be the most accurate values, so we can see there's some uncertainty depending on the assumptions that we make. But we believe that at least this gives us a like-for-like comparison to other studies doing similar experiments. We then exposed these residues to hydrothermal liquefaction. And unfortunately, we can see that the oil yields were probably not as high as we would have liked. So we get oil yields for 30% for our wet material, but only around 10-15% for our solid plastic containing material. And then if we look at the composition of the solids, what we saw is actually most of these polyolefins do not decompose at those temperatures. So initially, this is quite a disappointing kind of analysis. But if we flip this around, it also gives us the opportunity to now use HTL as a separation method. So we can break down the organic, the bio-based content. We can convert it into bio-oil. We can use that for even as a biofuel if we like, or we can use it as a chemical feedstock. But then we can use this concentrated plastics in a solid product, which is now a dry material, and feed this into other chemical recycling processes. So if we then look at the entire process, we can see this is the existing process on the left-hand side, where we are producing our waste residues, and we produce the feed into anaerobic digester. And then we have our new process where we separate this. And here we produce, based on the water that we use in the process, we can see that we use about 3.5 times as much water on the left-hand side to the right-hand side. So because we wanted to then see, can we recycle this water back into the waste, existing waste treatment process. So the first thing we need to then check, is this aqueous phase actually suitable for our biological anaerobic digestion treatment process? So we did some batch experiments. So this is just a baseline, and then we used the 3:1 mass ratio of our sewage sludge to our new aqueous phase, and we can see that the process still works. The yields are a bit lower, but given that we've got 25% of our waste material in here, actually our overall energy recovery is higher. And then we can produce an overall mass balance of the process, and we then model the system using process simulation software to see how much of the energy which was originally contained in our waste residue would end up in the bio-oil and in our biomethane product. And we can compare that to the energy use of a process, so we can see that we're producing a lot more energy product than the actual energy we need to put in. So of course, these products currently do not include the solid products, which contain most of the chemical waste, the plastic materials. So if we can then send these to chemical recycling process, we have the potential to really improve that energy balance a lot more. Okay, so the final area in our technology development is focused on selective plastic depolymerization. So in the previous work packages, we worked with biomass or mixed contaminated plastic. But here we want to work with cleaner plastic waste to produce selective chemical feedstock to feed the polymer or other chemical industries. And even though we do have mechanical recycling process for some of these plastics, actually in terms of polypropylene, only 1% of polypropylene in the world is currently recycled. This is partially down to the inadequate selection, contamination, but also the fact that you can only recycle propylene several times before you reduce the material property. So if we can break it down selectively, then hopefully we can use those chemical feedstock to make more useful products. So again, we need to develop a catalyst, and the catalyst then allows us to absorb our polypropylene onto the surface, transfer hydrogen and cleave those bonds, and then release our desired intermediates. Unfortunately, we can't just produce very precise precursors, but we produce a range of products, and really the products that we want are kind of in the, we don't want the short products, which are in the gas phase, and we don't want the very long products, which are kind of waxes, but we really want to target kind of a liquid and lubricant range kind of chemical products. So to design those materials, it's generally we use a combination of a catalyst support and our desired catalytic material. So in this case, we use ruthenium, but as you know, ruthenium is a very expensive metal, so we want to minimize the quantity of ruthenium that we use. So we do that by placing very small particles of ruthenium on a very large surface area. But what we can also see, rather than just the chemical nature of those catalysts and support materials, that the shape of a material can also be very important. So if we've got a large material, we might only have these kind of flat surfaces, but if we reduce the size, we now expose different planes of a material which might have different catalytic properties. So we wanted to then explore this by studying different types of shapes of a series support. So here we've got these long microneedles, and here we've got these nanocubes. And then we can test these at different temperatures to see how they affect the decomposition. So at low temperatures, of course, the activity of a catalyst is quite low, so most of our products are solid. But then if the temperature is very high, we produce mostly of a gaseous product. So somewhere in the middle, around 220 degrees, we get a very high selectivity to our desired liquid products. And we can see indeed that the type of the support, so whether it's got a nanorod or a nanocube, really influences then the kind of product distribution that we can get. So experimental work, of course, is very important, but it can also be very expensive. So this work, the experimental work is done at Liverpool, but it is supported by our team at Cardiff, who's doing molecular simulation to understand really what is happening on these catalysts. So here we have to simplify our reaction first. So we start with our polyethylene molecule, but then this is modeled in terms of pentane. And we can see that we've got 5 carbons, so we've got carbon in different positions. So we want to understand which of these carbons is the most likely carbon to actually participate in a reaction, and how does the support help to catalyze this. So what we then do is we simulate the absorption of the model compound onto the support. We look at the bond distances, and based on that we can then calculate the energy to form and break these bonds and create energy diagrams. And what we can see here is that going up means we need more energy. We have to climb this hill. So this work is then telling us that the most likely carbon to remove is the first one in the chain, so it really means we are unraveling those molecules from the end. And using that, we can then improve our catalyst design. Okay, so this was theme 1, and that was the technology development side. All this work is quite low TRL, and we were trying to develop new technologies. But what we really want to understand then is how do these technologies help us to transform our chemical sector? And this is where we're looking at the whole system approach. So to do that, we first look at process integration. We build our process flow sheets. We then combine these with life cycle analysis. And then finally, one area which is becoming increasingly important is not just to look at the environmental aspect, but also on the social aspects of this change. So if we create a process which is only affordable to certain areas of society, that is not really going to form a sustainable circular business model. I've already shown these diagrams, so really just to reiterate, this theme really sits in between the enabling technologies, so we can use the knowledge from the technology development and this finance, society, and policy, and it's very important to kind of take and communicate with these two different areas. So Andrea, in his presentation, will talk more about a case study which is based on sustainable ethylene production on the Teesside cluster. But here is a very rough overview of how we might go about that. So we might identify the product we want to produce, or we've got a waste and we want to work out what's the best route of what we want to produce. So there might be competing uses for a certain material. So we can create a process flow sheet or a range of alternative process flow sheets, and we model them, we optimize them, and that then gives us the basic information about the techno-economics. So how much does it cost? How much energy do we need? And this, of course, is very important. But then we can use the data from these models and feed them into life cycle analysis software, so like SimmerPro, using EcoInvent database to then estimate the different life cycle impacts from these processes. One of the difficulties with life cycle analysis is that we've got many different impact areas, and that can become very complicated. So we might want to try and group them into better impact categories, and then into the final kind of impact on the human health, on the environment, and on the kind of resource availability. And a popular approach is to then also combine that with kind of a global boundary system. So we say, well, we've got only one world, so if we use different categories, how much of this world would we need for this process? So one example would be the use of PM fuel cells. So we want to use hydrogen as a clean energy carrier, but we need a catalyst to help us to combust hydrogen. So the state-of-the-art material is platinum, which works extremely well. It's very efficient, but platinum is also a very expensive and rare material. So there's a lot of research going on in alternative materials. So for example, we've got here iron, nitrogen, carbon catalyst with a lower TRL level, but how do we now compare those two materials? So first of all, we can look at some of the performance data. So we see, well, platinum has a much higher power density. We need much lower catalyst loadings as a result. And because of that, of course, we also need much less catalyst. But the iron-based material is a lot cheaper. So from an economic standpoint, maybe this is acceptable. But when we put this through life cycle analysis and through our global boundary model, we can look at different impact categories, and we can see that the two materials behave differently in different categories. So as we would expect, platinum has a very high impact in terms of mineral resource scarcity. So we need a huge amount of platinum, which we can't provide. There's a high degree of acidification potential and freshwater eutrophication. But this new kind of cheaper material, or potentially cheaper material, has much higher impact in terms of human toxicity, global warming, and marine eutrophication. So to understand why this is the case, we then need to go back to our process model. And here is the process which is used for the production of this iron-based catalyst. And the first thing that stands out is that it's extremely energy intensive. So each of these steps requires large amounts of energy input, and our current life cycle analysis assumes that this energy is consistent with our current grid supply. And because our grid is heavily carbon-based, this then has a very high global warming potential. But we also see that it uses some, even though iron and nitrogen are quite harmless chemicals, we also use things like hydrofluoric acid in the production, which then can explain some of the other high human toxicity risks. And then you can look at the different impact categories, and we can see what are the key drivers for these categories. And we can see they're quite different for the two different materials. So for platinum, it's really that chloroplatinic acid, whereas for the iron-based catalyst, we've got higher issues with electricity and that hydrogen fluoride use. So one issue with all this analysis is the high uncertainty. We rely on databases, we rely on certain system boundaries, and this makes some of these kind of areas quite uncertain. And you can see there's even some areas which are very, very poorly understood, even though they do have an impact. But what we can still do is we can look at these, we can use them as a comparative tool, and then help them to drive our decision making. So as I said, Andrea will present about the T-side cluster in more detail, so he's probably better placed also to answer any questions about this area. But the final theme of our center is looking at the policy, society, and finance. And really, all the technologies is, of course, really important. We need to understand how can we solve these problems. But we also need to understand the systems and the non-technical challenges around that. So if we ignore them, we will never have a reasonable change. And these include why would business actually want to become more circular, and how can we encourage them to build more circular business models? How can we pay for this transition? What is the public engagement with the chemical circular economy? And this morning we heard a lot about public engagement with the textile industry, but the chemical sector is a lot more removed from consumers. So the textiles we interact with directly, whereas a lot of the chemical stuff is kind of happening behind the scenes. And then, of course, what do we need to change? What policy do we need? So in terms of circular business models, we conducted a range of case studies where we really want to understand how does becoming circular affect your business model? What are your drivers, or what are the challenges to increasing the circularity of a business? And how does it depend on different actors? So it's a very complex, interwoven scheme. So how do we work together across different industries to facilitate this transition? So we conducted 3 different case studies. The first one was working with Unilever and Lanzatec, who have developed a technology to produce a detergent based on carbon captured from the steel industry in China, and they are able to ferment it and convert it into this new surfactant, which has been launched in 3 countries. And actually this surfactant has had a lot of positive feedback, but also at the moment it doesn't make any money for Unilever. So they are spending a lot of money to develop that, but they're not financially benefiting from this change. The second case study was looking at chemical recycling, so where BASF is looking at a more sustainable feedstock as a refinery feed, and they're working with a range of chemical recycling companies to convert post-consumer waste plastics into this refinery feedstock. And the final one was looking at a Scottish company, Celtic Renewables, who is using ABE fermentation, acetone butanol ethanol fermentation, to convert distillery wastes into ethanol, butanol, which can be used as fuels, but also as chemical feedstocks. So there's some general takeaways that we learned from this. So the first one is that the circularity requires multiple companies coming together and working together. And this is really important. So how do we create these collaborations? And within those, different actors play different roles. So in the first case study, Lanzatec was the technology provider. They were really the ones that enabled this change. But we need to understand who's taking that role and why are they taking that, and how does that role change over time. Another very important point is that both benefits and risks are not evenly distributed. So some of the Lanzatec would have made quite a lot of money from this original project, whereas Unilever was doing it, but they were not benefiting financially. So whilst this might work for a couple of key products, it is important to understand how can you change this balance to drive further change or broader change throughout the industry. And scale up is another issue, particularly with the last study. So how do you develop the technology, and how do you then move towards industrial scale production? Another area we look at is on the finance side, and of course we have some investment in circular economy, but this needs to grow quite substantially if we are able to deliver on our carbon budget. And we can see we've had some growth already over the last few years, but at the moment this represents a very small fraction of overall investment. So it is trying to look at what are the existing business models, what are the new circular business models, who are the different funding agency, what what motivates them, and then what are the tools to use the funding. And here again, we worked with a couple of companies to try and understand how did we come from technology development towards full-scale production. So here, Celtic Renewables was actually launched in the 2010-2011, but then it took them over 7 years to get the industrial backing to create a commercial process. And within this time, they actually successfully acquired government funding, but then they lost it because they couldn't get the in-kind, matching support. So because of that, actually that made the situation worse. It's quite difficult. How do we get through this valley of death? Okay, so the last area that I want to quickly touch on is the social dynamics. So to try and understand consumer engagement with circular chemical industry, we conducted a large survey of 2,600 participants, and we try to understand how do they what do they understand about the circular chemical industry, and are they willing to actually take more circular decisions. And based on the responses, we can group our respondents into different categories. So we've got some of these, what we might call green and proud, which is about 10%, which are generally younger, well-educated, people with a good income. Some that want to be green and they can actually afford it. Again, here we're talking about some of the more affluent parts of the population. The positive majority probably supports kind of the circular economy thinking, but they might not be particularly adapt their lifestyle towards that. And then we've got some of the population that doesn't believe in this idea at all. So this is some of them less educated, older parts of the community. And based on that, we can then see what's the awareness of the chemical industry and of policy. So most of the groups actually have quite a low awareness, as we might expect. So that tells us maybe we need to raise this awareness. And what's the attitude towards different areas? Do they believe the advertising? Do they trust what's written on the packaging? Do they care about the environmental issues? And then very important is also, are they willing to pay for a more circular product? And of course, we can look at the good economic conditions where maybe we've got a fifth of the population, but in the current conditions where living costs are extremely high, the willingness is significantly reduced. So we're still analyzing this result and then trying to work out what kind of campaigns or actions we need to take to try and shift some of these opinions or create a demand for more circular technologies. So the final thing I've been asked to advertise is our summer school, which will happen in Newcastle in September. So it's a free day event. You can find the information on through the QR code, and I believe Rose, our engagement admin, has also been handing out little sheets with more information. And one of the key focuses will be on LCA and some LCA training during this event. So finally, I'd like to thank, I haven't listed all of the contributors, there's quite a lot. So of course I wanted to thank particularly the 3 theme leads whose slides I've stolen. So that's Alex Kahn from Liverpool, Benoit Chachuat from Imperial, and Bing Xu from Heriot-Watt University, but also thank you for staying. So I don't know if there's any quick questions now. As I said, I'm probably not the best one to talk about the LCA, so if you've got any questions, use the chance to ask Andrea, who's working with Benoit and Imperial. But if there's any other questions, I can take them now. If not, I will hand over to Andrea to tell us more about the Teesside sustainable ethylene production.
So good afternoon, everyone. Okay, the light is a bit, it's very strong. So I'm Andrea Bernardi from Imperial College, and I will talk about a specific case study, a set of case studies actually, about ethylene production, and mostly about life cycle assessment. So we all know that we are producing a lot of waste so a lot of plastic and a lot of plastic waste, and the big plastics like polyethylene, in particular low-density polyethylene, for example, is also not very widely recycled. And in the UK, for example, we use 5 million tons of plastics every year only for packaging, and nearly half of this 5 million is for packaging. But packaging has also a very important role, which is to extend the lifetime of food and hopefully reduce the food waste, which has much higher impact than plastic waste. So we still need to keep at least some of the packaging. So one idea could be to have some sort of reusable packaging material, and we work with a company on this. It's a small startup company, and basically their idea is to have a food pouch that you can use and then return to the packaging provider that essentially wash it and resell it to the food producer. And the idea itself has potential, but we need to quantify correctly the impact of this kind of return or reuse scheme. And in particular, even though we can use this pouch like hundreds of times, whenever we introduce the fact that the return rate will not be 100%, even if we have a 90% return rate, which is quite high, on average we use a single pouch only 10 times. So this really puts the focus on the consumer behavior and also the adequate infrastructure to have a high enough return rate. Otherwise, essentially the average utilization will not be high enough. So I go back to this slide because if we want to have a more sustainable plastic, we need to start from the raw materials. And to have raw materials, we need essentially a source of carbon. And in the UK, there are different sources that we can use. There is, for example, biomass. The UK is a big wheat producer, but we also import a lot of soybean. Most of the soybean used in the UK is imported from South America, and a lot of it goes into animal feed. So there's kind of an imbalance here. As I mentioned, we have a lot of plastic waste, and we have roughly 1.2 million tons per year of packaging that is being recycled, which is not too bad because it's roughly half. And then we can start from CO2, but we need either a bio-based source of CO2. For example, bioethanol plants produce CO2 as byproduct. Not too much. It's like 5.7 million tons per year in all Europe. Biogas plants are a bit more, produce a bit more. And then there is direct air capture, so capturing CO2 from the atmosphere. Nowadays, essentially doesn't exist at big scale, but it's getting traction. And here we have only predictions for worldwide CO2 direct air capture. And we are talking about something between, let's say, 5 and 50 million tons per year worldwide in 2030. Now, when we look at ethylene, we focused on the Teesside because there is a big ethane cracker from SABIC and produce 800 kilotons per annum of ethylene. And there are different ways we can make this ethylene production more sustainable. One way is to keep the business as usual, so still do ethane cracking, but we can either capture the CO2 Or we can electrify the cracker itself. So instead of delivering the heat required with methane, we can deliver it as with green electricity. Or we can start from bioethanol and then use catalytic dehydration of ethanol. Or we can do some sort of chemical recycling. And in this case study, we consider pyrolysis of polyolefins. Finally, we can start from CO2, but as John mentioned, the TRL level is a bit lower here, and we need essentially a reliable source of CO2 and a renewable energy source. And wind is essentially the best option, especially in the UK. Starting from the first one, so when we look at an existing steam cracker, it's like a very complex system. There's a big diagram there. I don't want to go into details, but essentially, whenever you change something, you basically break down all the optimization that has been done around it. So what we did was to estimate a steam cracker at scale and compare business as usual, which is on the left, with a case where we capture the CO2 and a case where we have an electric cracker. And what we found is that when you simply add carbon capture, you increase the overall energy demand. So you need to be careful if it's really a good thing or not. While an e-cracker can be significantly more efficient, so use roughly half of the energy. But this, when you scale up to a sub-X size kind of plant, you will need 4 terawatt-hour of electricity, which is quite a lot. Plus, the savings in CO2 emissions will depend on the carbon intensity of the electricity that you use. And we can see on the graph on the right here how these savings goes down. And if we have enough wind energy, for example, we can significantly reduce the carbon emissions. But if we need to rely on grid electricity, we don't reduce it as much. Now, on the other hand of the spectrum of this scale of TRL levels, we had a look at electrochemical routes. And here we compare different routes that are either purely electricity-driven or partially electricity-driven and partially thermocatalytic process, keeping a maximum of at most one intermediate. So we can go through methanol or through methane or through CO. And we did a similar study. We had a look at the costs. So here we found that the cost will be significantly higher, roughly 3 times higher for the best case scenarios. And most importantly, when we scale up the process and look at the inventories and the amount of electricity that we need, here we are going to need much more electricity, 1 order of magnitude more. With the best case scenario here being the e-cracker, and it's still going to require 47 terawatt-hour of electricity. Now, when we compare this with the electricity generation in the UK and the renewable electricity in particular, we see that it's probably not going to be feasible because the amount required is essentially too high. So there is a take-home message here. So one thing is doing decarbonization of the chemical industry, another is defossilization. And there's an energy penalty to pay there. And so we need really to figure out reliable and hopefully cheap sources of renewable electricity. And a similar conclusion has been achieved by in this recent report from the Royal Society, which was talking about net zero aviation, but essentially their conclusions are similar. So there's not a single winner, a clear winner, and probably we will need to rely on a portfolio of alternatives and also try to find ways to evaluate the CO2 to enhance the competitivity. Now this leaves us with the last 2 options, and here I'm going to just show the LCA results. So we can have a look here at a simplified block flow diagram of the 2 options. And a key point to make here is that both the ethanol production and the plastic pyrolysis have not only a main product, being ethanol and ethylene, respectively, but also a set of byproducts. And in case of ethanol, we have this DDGS, which can be used as a soybean meal substitute. While in the plastic pyrolysis, we have another set of hydrocarbons that also has a market value and can be sold in the market. Now, in LCA, when you have multifunctionality, something that has been mentioned during the first day of the workshop, you need to take this into account, and there are different ways to do it. And what we usually try to do is use system expansion, where essentially you give to the process some environmental credits, because they are going to displace a product that would have had to be produced in other ways. So a key assumption here is that there is a market for the product. So it has to be a product that you are actually selling to the market and not creating without any reason. And this is particularly important when you scale up the process and look at the big picture of how much you produce, how much is required from the market. Jumping to the results of the life cycle assessment, first thing to look is global warming potential. And here we have different alternatives. So on the bottom of the graph are some results from the literature. So the first two on the bottom are essentially the business as usual, naphtha cracking and shale gas cracking. And then going up, we have our alternatives. So we have the last four on the top are bioethanol-based ethylene. So we can see that the wheat is doing quite well, but we need essentially to have a market for the DGS, because otherwise the impact will be essentially the same as the business as usual. While plastic pyrolysis is roughly the same as the business as usual in terms of global warming potential. And finally, CO2 electrolysis has a big potential because it also has a negative global warming emission. Now, focusing on the biomass. So the biomass-based route has a key raw material, which is wheat in this case. And we can see that in the UK, the global warming potential of wheat is low compared to other European countries. And then we have a key byproduct, which is this DDGS. And as I mentioned before, most of the DDGS is imported, so the UK has a high impact for soybean. So it's important to displace that imports. And going back a little, we can also look at why the impact is high or low, and essentially the majority of the impacts come from fertilizers and fertilizer degradation in the soil. The conclusion here is that wheat-based bioethylene looks quite good, but because we are in the UK, but this performance is highly country-specific and depends on the particular circumstances. Now, global warming is just one of the impacts that we can look at. There are several others, so-called midpoint indicators. We can't go through them all, so what we usually do is there are methods to aggregate them in these three areas of protections: damage to human health, damage to ecosystem, and damage to resource availability. And we can look at these three impacts for our four alternatives. And for example, we see that now when we take the damage to human health, the bio-based alternative is actually performing much worse than business as usual. This is mostly done because it emits a lot of particulate matter. If we go on another environmental category, which is damage to ecosystem, now wheat is going back to be a good alternative. And finally, when we look at resource availability, we see that essentially all the routes are using less resources compared to business as usual, which was somehow expected. Now, we can further combine these three by applying some economic penalties to these indexes and come up with the so-called externalities cost. This, of course, adds an extra layer of modeling and an extra layer of uncertainty. That's why the uncertainty bar kind of explode here, but give us a way to compare the different alternatives overall, with the overall environmental performance. And we can see here that combining all three together, the wheat-based alternative is very similar to the business as usual, but has a very high uncertainty around it, while plastic pyrolysis has a good potential, but we need essentially better models because we used very simplified and very optimistic model here. So there is potential, but we need more detailed models to see how much of this potential can be actually delivered. And we can identify key areas of intervention. For example, for the biomass-based route, we need to understand why this particulate matter is so high and how we can reduce it. And finally, let's go back to the available resources. So one of the first slides I showed. And here I'm just reporting the numbers again, but it's not very important to remember the numbers because I have this graph that illustrates the available resources. And just a reminder, the CO2 is available either overall in Europe or in the world, while the other figures are UK specific. Now, when we scale up the production for a SABIC size ethylene plant, we can see that we essentially need a third of the wheat in the UK, and we can displace half of the soybean imported, and this last bit could be a good thing. We would need an amount of plastic that is currently higher than the total currently recycled, and we will need also a very big amount of CO2. And if we scale up even further for the UK production, because the UK has 3 crackers, then we essentially exceed all available resources by quite an extent. So the conclusion is, again, there's not going to be one single solution that is going to substitute all fossil-based ethylene. A key area is we need to reduce probably the total consumption and through other mechanisms like reuse and repurpose, and then essentially combine all the possible routes that are available and economically feasible. Thank you for the attention, and yeah, here's my email if you have questions in the next days, but if you have questions now, I'm happy to take them. Yeah, I can't read. I think there's a question there.
Hi there. Thanks, Andrea. I mean, I know this was mentioned at the Circular Chemicals Showcase, and I'm glad you added the last sentence there because that wasn't mentioned at the Circular Chemicals Showcase, that none of these routes really seem feasible, and therefore we need to reduce consumption. But how much is being done in the centre on, I mean, it might be not a question for you, on that question, on whether it's really feasible? Because most of the projections are, let's grow this industry more and more and more, yet we don't seem to be able to do a sustainable route to what we're already using.
Yeah, it's definitely not a question for me, but no, I think, I mean, it's a good point. So it's not what it's not my area of expertise, but yeah, essentially, what we can do is quantify what would be needed and how much we should reduce, essentially. And then, maybe the people from Elliott Wood that looks at business model can have better answers. Is there a question? I don't know. Can't really see with the light.
Maybe not. Yeah, that's a great question, Amy. Thank you for that. I actually think I thought a similar thing this morning in the last session on the this new consumer engagement group, if I got it right. And I think it's definitely something we should be engaging with. I think where we position ourselves, we're trying to create the technology solutions, but I think that reducing consumption will form a key impact, and we need to reconsider the way that we use the resources that we've got available to us. Okay, if there's no other questions, let's thank Andrea again. And then I will ask Katie Lam from Sheffield to come up, who's going to talk to us about the policy side of the centre. Actually, very sadly, Katie will be leaving us in a couple of months' time. She's done a really great job over the last couple of years, or 2.5 years, even on the centre. So it will be maybe our last opportunity to hear from her today.
No pressure now then, eh? Let me just get myself sorted. I'll just have a quick drink of water. Well, good afternoon, everyone. Thank you for staying, and thank you to those who've especially come today to hear about the Circular Chemical Centre, and thank you, John, for your kind words there. I'll try and give a good presentation. So, as John's already mentioned, I come from the theme-free part of the centre, so I work in policy, and today I'm going to talk about my research project, which is titled on the slide here. So it's developing evidence-based policies for the implementation of the circular economy in the UK chemical sector. And in case you're wondering who that skinnier woman is on the slide with the shorter hair and no glasses, that was me before the pandemic, so take it for what you will. But it is me, I can assure you. Okay, so just to start off, I'm going to give a quick overview of what I'd like to discuss today, and I'm going to discuss my work in sort of four themes, or in four areas. So first I'll talk about how policy and what it is, and say where that fits into our centre. I'll describe my research aims and methods I've been using during my time with the centre, work that's currently ongoing and outputs that I have done so far, and hopefully have time at the end to discuss where we'd like to have some more potential collaborations with those of you in the room and those of you already in the NICER programme. Okay, so as John's already nicely mentioned in his talk today, I don't need to be on this slide too long. I'm in the theme-free part of the Circular Chemical Centre. So there's a large part of people at the Harriet Watt team looking at the business, finance and public and society side, and I fit into this tiny bit of it here, which is in the policy-making side and engaging with government. Now, I never like to assume that people that come to my talk know definition of policy, so apologies to those of you in the room who may know this, but just so we're all on the same level and playing field, I'm just going to briefly describe what policy is and also how it compares to legislation and regulations. So policy is different from law and of course regulations. Essentially it's a guide. So essentially if you by 2050, as I hope we all want to be all net zero by 2050, we're not just going to get there without having a guide and having ambitions and actions to drive that. So policy can help get us there. Now, on the surface, it may look similar. Policy and law may look very similar, but actually they're quite different. So, of course, policies will be used with law, and law itself is used to implement justice and order. And, of course, policy must comply with existing law. But there is a definition difference between the two. And, of course, if a policy is good, it can lead to the creation of new laws as well. So that's very, very important to say. And, of course, policies must also comply with regulations, and these are usually things in place in businesses and that essentially lead to action, so on and so forth. So hopefully that's given you a good background. I must admit this is a very brief and quick background information about what it all is, but hopefully that set the scene for you. So, what are my research aims? So, one of the research aims is to evaluate performance of competing technological pathways, a little bit similar to what Andrea's talked about, but also alongside policies to essentially inform new policies. So, what policies are currently out there, what policies are on the horizon, and how can this help drive a circular chemical economy? And we've seen this picture loads already today, but how can that be used to effectively drive these different routes that we're looking at in the Circular Chemical Centre? One thing I learned starting this all actually is that as with policy, it does not have to be based on any data or evidence. You can, if you want, go and write a policy that is purely opinion-based. We don't want to do that. We want our policies or any policies we input into to be evidence-based. So we want to use as well as we can data and all that whenever we are looking into making new policies. Now I know there's obviously problems when it comes to using data. Is it reliable? Is it freely accessible? How old is the data, etc., etc. But we still, as much as possible, want to use data as well as we can. And a big overarching aim in the future of all this is actually not just to inform current policies and future ones, but if possible, devise new evidence-based policy instruments with the overall aim of stimulating supply, demand and investment towards sustainable chemicals. So just to give a rundown of how I do this, one way obviously of doing this is making sure we know where we are at the minute. So one of my methods is actually looking at policies that are already out there. So in case those of you who have not heard of this word before, one thing we really have to consider when it comes to UK policy is devolution. So since, I believe, shortly after the early 1990s, it's now possible that Northern Ireland, Wales, Scotland and England can set their own policies and laws if they so choose to. So if you ever hear the term devolved laws, that means it's a law or regulation even that's been run only in a little part of the UK, not a little part, sorry, a particular part of the UK. Whereas if you hear the term reserved, it means that all parts of the UK have decided, okay, we'll all use the same method moving forward. And these are just a few examples on the slide here. So, of course, these are not the only 4 policies out there looking into circular methods and stuff like that. But in my role, I've been looking at what different parts of the UK are doing and trying to see what works well, what doesn't work well moving forward. And, of course, I know that I'm working on UK policies, but we don't want to just see what the UK is doing. We want to have a broader global look. So this has taken a fair bit of work, but I've been looking obviously at global policies as well. So obviously, sadly, after Brexit, I keep an eye on what the EU are doing with the Green Deal, the Circular Economy Action Package, and they're doing a lot at the minute into plastics, especially at the minute. And America recently have launched the Inflation Reduction Act, where they hope to reduce inflation, and any money they save is sent towards green sustainable routes, and so on and so forth, and there's loads more. And actually China was very forward-thinking with road mapping, which I didn't realise when I started this work. So I know often we look at Western-based policies, but it's good to also see what the world is doing. So that's one thing I've been doing in my work. And when it comes to looking at these policies, I just want to briefly describe the techniques I've been using, or the analytical methods, in case anyone here is interested, because I would like to encourage you to do this yourselves and look into policy. One is SWOT analysis, so essentially you look at the policy, what are the strengths, weaknesses, where are the opportunities and what are the threats. More detailed dive is what's called pestle analysis. So what are the political implications of this policy? Is it economically sound? Is it socially acceptable? Is the technology there? Is it actually legal, or is there going to be future problems with that area? And does it actually impact the environment? And a simple other one that we look into is also gap analysis. So is there any current gaps in the policy? Can it be filled? And if it can't, why not? Etc, etc. And also one thing we're quite keen to do in the centre is use theory of change. And this ties in a lot of other people's work across the centre, coming on social impact measurements and all sorts of things. But whilst we're doing this work, we don't want to just set a goal at the start and say, right, we want this policy, let's go, and off we go. The world has changed a lot since I started this project. I didn't imagine when I started, sadly, we'd have the conflict in Ukraine going on at the minute, and more pandemic stuff that's been going on. So we use theory of change often in our centre to reassess the situation and use that to make sure we don't actually not deliver on our own goal at the end. And this ties in with PERT analysis, which is project evaluation review techniques. So essentially, you set your goal, and then at certain times throughout your project, you evaluate how well are we doing, are we getting there, or do we need to reassess what we're doing. And we also are using much more. This is just a selection, and also we also want to devise our own policy tools in the future as well. And one thing I'd really like to mention is social responsibility, which I've already hinted at. We can't just focus on carbon emissions. We have to think of the bigger picture. And I don't want to adopt, as sadly I come from a carbon dioxide chemistry background, and I think I sadly did have a carbon tunnel vision, but I think we should not go down this route of having one. What do I mean by this? Well, I came across this figure shortly when I started my role on LinkedIn by Jan Konitsko, who's brilliant at creating infographics on this, and essentially he very well illustrated that if we focus too much on carbon emissions, which don't get me wrong, we need to focus on, you may inadvertently actually cause problems elsewhere. What if by, for example, you solving the CO2 issue, you've taken all the water, say, from another country, or you've dumped a load of toxic waste somewhere that's not on your doorstep, so on and so forth, or you may even create inequality. So we use this in our approach as well, so we always think of the social side when we look at policies, and we want to use that moving forward. And I'm happy to share these slides, so if ever you want to get a link to the original picture, I'm happy to share these later on. So hopefully that's given you a good policy definition overview and a good overview of what I'm hoping to do and what methods I've been using. And now I'd like to dive into 4 particular areas of current outputs and work. So firstly, I'll briefly talk about a journal article I did, then reflect on the deep dive I did into COP26 and a little bit on COP27, discuss responses to online consultations, and then go into some big piece of work we're working on called carbon in the circular economy. So when I first started out in this role, obviously, as I mentioned earlier, I looked into what is the current policy atmosphere. But we also decided to look back a little bit. So what was the picture before I started my role? And because COP26 was on the horizon and actually finished shortly after I started my role, how has that changed the policy landscape? So I'm only going to briefly discuss this today, but there is a link to it and it is published now on the Frontiers page, and I'm happy to disseminate this paper afterwards. But essentially we looked at how policies before and after have changed as a result of COP26 and set out our own vision of how we think we need to get away from the linear model in our policies, be more circular, but also not only incorporate decarbonisation but defossilization. So I appreciate that's a very brief snapshot of it, but I'm happy to discuss it with anyone if you are interested. Following on from that, I did a much, much deeper dive onto COP26 and 27 because, of course, we hosted COP26 up in Scotland, what feels like quite a long time ago, but not that long ago now, actually. And we thought whatever comes out of this will really drive future policies in the UK for a while. So I went away and looked at all the different policies raised and produced this report. This is on the CircularChem website as well, but again, I'm happy to share these slides so you can go and read this. And essentially, when I did go to look at this, I was going with a chemicals angle. I was like, right, what's the future of chemicals? And sadly, chemicals wasn't really mentioned as the sector. It was sort of done on the mantra of cash, coal, cars and trees. So sadly, there wasn't much to say about the chemical bit, but we thought, well, okay, let's have a look at the mantra of COP26 and see what comes out of it. Now, I'm not going to go through all these numbers because I'm trying to tease you into going and reading the report for yourself. But essentially, obviously, because I'm using evidence and numbers when analysing policies, I looked into each of the 4 mantra and all the promises came up, and I came up with these numbers that showed the good sides but also the bad sides of it. So please go read the report, or by all means take a photo, and if you want to try and guess what the numbers mean and quiz me later, I'm more than happy to see if you've guessed. And I've only very briefly put up the image of COP27 because by the time we'd done this deep dive, it was just around the corner, and we thought, well, let's see how things improve, but sadly we think things really didn't improve too much, and in fact, especially with coal, it went a little bit backwards, so that's mentioned in the report as well. But yeah, so sadly I think we set good ambitions, but I think we're still not quite there. We need to go further. However, I've just put this image up because I realise it's very easy for me to stand up here and critique that, oh, we didn't deliver this at COP26, we missed out on this. Yeah. But I think even this image is very simplistic when it comes to really showing the complexity, when it comes to policy and, well, research and anything in general, really. So it's easy for me to stand up here and say these are the problems, and I think we should state the problems, don't get me wrong, but imagine if I was in Alex Sharma's shoes of saying what should we do at COP26, I don't know if I would have known what to have said, so I just want to state that anyway. So that, to make it clear, I appreciate it's complex. Okay, so that was COP26 then. Throughout my role as well, obviously, it's been about collaboration and actually engaging with government. So if you're unaware, a lot of the time, government actually do run online consultations. They may not advertise it very well, or at least in my opinion they don't. But if you go looking for it, there's loads of opportunity to go and engage with government. So some examples I came across in my role is there's a great incentive called Post, where they go and produce what's called post notes, where it will literally be 4 to 5 pages for something that MPs read, and will really summarise a complex issue, very short and very sharp with lots of data. And I contributed to a green steel one because it tied in a little bit of what I was looking at and past PhD research that I'd done. And I've done other responses to committees, so you can go into the UK Parliament website and see what committees are looking for. So there is the Energy and Environment Audit, I might have got the words wrong there, but there are specific committees that look at particular issues. So me and other members of the Centre collaboratively have submitted responses to these 2 calls during the time of me being with the Centre. And most recently, one I really like to highlight is there was one that came out not long ago on just transition to net zero Wales. So we inputted onto this, and I also worked with other people across the NICER programme. This wasn't just a CircularChem response. And very recently, very promisingly, Northern Ireland have launched their first ever circular economy strategy, and they actually wanted feedback on this because, as I'm sure we're all aware, they've got their own issues going on with the Irish board and everything, so they're quite honest when they come and say, sorry that we're slow at this, but we've had other urgent things going on. But they are trying to catch up now. So we have responded to this, and we hope to see how our responses have helped drive this change as well, and look forward to seeing how these consultations have gone. And finally, the last bit of work that's ongoing, so I've mentioned a lot of my outputs, but I want to quickly go on to something we're currently doing, and I imagine the centre will carry on once I'm gone. And it's looking actually more specifically into carbon and the circular economy. And this is quite nice, already been hinted by John when you mentioned the carbon footfalls. And I think we all know that we can't only just get CO2 out of the atmosphere, we have to think about the carbon and all the things we use. And I came across this great figure not long ago, and there's actually an updated figure out there that takes into 2022 now. There's a company out there called the Renewable Carbon Initiative, and they work with the Nova Institute, and they went and scanned the whole chemical sector globally and devised, well, okay, where does all the carbon for these come from, and how's the picture looking? And they were able to estimate how much carbon per year is actually in the chemical sector, and it turns out 85% of our carbon is still currently fossil-based. And even when they revised these numbers recently, I think it's still sat at 85. So, and there's only 10% bio-based, and 5% is only currently cycled. And I guess tying into the question we had earlier about, well, why we need to push to reduce our use, which I agree with. Sadly, in the same report, they actually tried to predict, well, what's going to happen in the future of the chemical sector, and actually our demand for this, they predict, is only going to go up and up and up. So yes, I agree we need to reduce that. The minute, unless we change our tact, we're actually going to end up needing a lot more carbon. And I won't go into this figure fully, but if you read the paper, they predict that it will go up, and there's nothing they actually argue it won't ever go down, but they've devised routes where they think they can get more recycling in there. So I do urge you to go read this report, but I'm not going to delve into that too much today. Well, essentially, we're very interested in this as a centre, because carbon is very important for chemicals, and this is just to reinforce we do need it. We're sadly never going to not need it unless something drastically changes. So we must focus on both defossilisation and decarbonisation, and this ties in with what Andrea said. Of course, they both have their own issues, but we need to collectively use this and other techniques. But it's complex. Again, this doesn't show the whole picture, but ICIs have this powerful image of how the petrochemical sector actually looks. And I mean, something that I can't even read when I have the figure open on my computer. It's really, really complex. How can you trace all that carbon? How on earth do we make this circular? And although it's ambitious, this is something the CircularChem in the long run really want to tap into, because although it looks scary, unless we do dive into the deep end and look at this, we might end up not really addressing the issue at all. So to try and learn more about this, an early stage thing we're doing is talking to you all and talking to those in different stakeholders in different sectors to try and gauge, well, is there a way around this, what's currently being done, or do we need to devise a new methodology? So we've come up with a set of interview questions, and I must say Matthew's not here today as he's actually currently on holiday, a well-deserved holiday, but he works at the Newcastle team, and he's working a lot on road mapping, and because I saw that what I was doing on this with policy and all that overlapped with his work, we thought we'd work together. And I must admit, I did nick this figure off him, where I think it really powerfully illustrates, we need you. So we've talked to some people, we want to talk to more people, and when I go, I imagine they'll still want to carry this on. So if you are keen in this area, or if you think you've got some answers, please do approach us about that. So that's all my current work and outputs, but I guess there's one thing, if I've learned in my short time in policy, because I must have said I come from a chemistry PhD background, I've only been in policy for years, I guess if there's one thing I can pass on before I do move on, it's do please engage. There is more options out there than you think. It might not be initially obvious, but you can get weekly or even daily government.uk updates on policy changes. Do go look at Postnote, look what what all parts of the UK governments are doing, so Scotland, Northern Ireland and Wales. And there is, it depends if you want to see people in Parliament arguing all the time, but you can actually go and watch what they're debating and keep an eye on what's on the sphere. Because, if obviously you're researching something and then they're debating about it in Parliament, that might be your opportunity to get in. But as you may have noticed, I've said engage correctly. I guess I've noticed more and more in this role that a lot of people say, well, policy needs to change, but then when I've gone and asked them, well, what do you mean by policy, or what's wrong with the current policies, a lot of people can't answer my question. So when you do, I think, just mention that policy needs to change, I would make it quite clear you actually know what you're saying. I was guilty of this when I started. I just said, oh, policy needs to change. But then when I've had people in government say, well, which policies? I went, what do you mean? I wasn't too sure. So make sure you know, but do actually engage. We all may be busy, but unless you go knock on their door, they might not come to you. And it's easy to blame other people. I liken this to a bit like a football game. It's very easy to watch football and scream and say, oh, rubbish, rubbish, when it's all going wrong. But you're not the one on the pitch playing the game. So there is lots of complex issues and there's things need changing with government and things going on, but there are a lot of people on the ground in the civil service really trying their damn best to address this issue, but also things like levelling up and lack of money and energy bills. So don't go with that attitude when you go and speak to them. You know, we've all collectively got to get there together, so don't go in with the blaming attitude. And finally, just to end up, obviously there's lots going on. I've already mentioned the carbon and circular economy paper. Please do approach me or anyone at the centre if you're interested. We are planning to do policy workshops and discuss things across the whole of the UK, not just in England. And there's loads of other things going on, obviously, in the sphere regarding olefins and plastics and chemicals and more. So yeah, do approach us for collaboration. And if this is the last time I get to speak, I don't know if it is, thank you ever so much for a great time with the nice programme. I'm here a bit longer, I'm here till the end of July, so here's my email address. And I'd like to thank everyone at Sheffield on the team that's helped me, and thank you all for your attention. Thank you. I have gone over. Oh, there is a question. Okay. This is one I can't see who it is. Hi, Tom.
Thanks, Katie. Thomas from RAP for audience reference. I just want to touch on a point that Andrea made and that you sort of pointed on as well, where you added in the comment about trying to reduce, and then you added in the graph where you said, actually, we don't think people are going to reduce. And the D words, defossilization, decarbonisation. And another one I see a lot, which is decoupling, where it's GDP growth and material kind of consumption. Everything is always growth, like the line must go up, essentially. It has to go up at all costs. And it's the externalisation of those costs that are the issue. And are we having enough conversations about that element? Because we are talking here about wheat and soy and all these new resources that we can exploit. But we have to go down. I mean, there's no question there. But a lot of these are just talking about how we can take other resources and waste. Fair enough, I'm in support of using waste more. But are we doing enough there? I'm hesitant to ask how do we do this because it's too big a question. But what do we need to do next? Because there's a lot of moral implications here that aren't touched on in a sort of scientific sense when we're looking at these numbers and figures. So just thoughts, really.
No, I completely agree with you. I think it comes down to, I think a lot of people are coming along with us on this whole green mission, but I've had talks with even my family members where I've said, well, actually, do you realise being greener might mean we have to use more resources and damage the planet more? And they look shocked. So I think an element of it is we've got people on side on the green bit, but we need to either really convey to people, well, do you actually want a green life or do you want more? And try and get people to understand the two. I do think it is important. I've looked at it a little bit, but I can't say I have. I do think the team at Heriot Watt are really trying to look at that on the social side, because I think a lot of that lies there. You could write the best case scenario and predict, okay, if we decouple, then we'll get to here. But if the public are not on side with you from the start, or if, sadly, it sounds like you're saying to them, you can't have a good quality of life, we're not going to get there. So, I think it's a great question, and I think it does need to be discussed more. I agree with you, Tom. And hopefully there's people in here in the social side who can address that question better than me. But I do agree with you, it does need to be discussed more, otherwise it may make us fall at the final hurdle. Oh, sorry, I can't see it all. Okay.
Thank you very much, Katie.
Thank you.
Very good talk.
Thank you.
Okay, so this is our last presentation, and I think the last presentation of this showcase. So I think there's a presentation, a video afterwards. So Swathi is actually a postdoc researcher who works with me in Loughborough, and she did that work on catalysis of for HTL, which she presented. But she's presenting on quite a different project based on a secondment she did with RAP last summer, and she's just finalizing the findings from this work. So over to you, Swathi.
Thank you, John. Hi, everyone. I'm Swathi. So as John introduced, I work with John at Loughborough University. So I'm basically an experimentalist in the lab most of the times, and I got a very good opportunity last year to work with RAP on a secondment project. It's a short one for 3 months, but I'm still working on the report. There's lots of learning from this project, and I'm just showing a few slides here. So this project is on proposing recycling technologies for the residual waste from the construction and demolition sector. So the aim of this project is to review the options for improving the management and also resource recovery from the residual waste from C&D sector. And so this presentation would go like, so initially I would try to say to understand the quantity, source, and the destination of the waste, and the composition, and then review the available technologies to treat the waste and implementation methods and some recommendations. So just to start with, residual waste are non-hazardous waste materials which cannot be recycled or reused, therefore they go to landfill and incineration. And residual waste can be sorted as mineral waste and non-mineral waste. So mineral waste are generally the soils, aggregates, bricks, which are minerals. And the non-major mineral wastes are mostly organic, but it also contains some minerals, but then mostly they are organic materials. And it's separated to 4 main sectors, which is municipal, CD&E, which is the construction, demolition, and evacuation, C&I, which is commercial and industries, and finally AFF is the agriculture, fisheries, and farming. To start with, looking into this Environment Improvement Plan 2023, we have few targets on waste management, such as eliminating the avoidable waste while achieving a 2-fold increase in the resource productivity by 2050, to reduce the amount of biodegradable waste and also the plastic waste that goes to landfill, and to eradicate the waste crime by 2042, and also to reduce the amount of residual waste, excluding the mineral waste. So we are not targeting the mineral waste generated by per individual by 50% by 2042. To achieve these targets, we have 8 interim targets to be achieved by January 2028. Out of 8, the first 2 targets are focused generally on all kind of residual waste, non-mineral residual waste from all the sectors. And the other 6 are focused only on the municipal residual waste. So why am I focusing on construction waste? If you look into the residual waste that goes to landfill, I think the percentage, the ratio of municipal to C&D is 80:20, so municipal waste is quite high. But then I focus on construction waste, particularly because of the environmental impact. And also there are lots of new legislations for handling the municipal residual waste, but the construction waste are often not looked well. This is the waste data from 2018. So out of the 222 million tons of waste produced, 138 million tons are from the CD&E sector. Even though C&D sector has a very good recycling rate of about 90%, about 5 million tons of waste from the C&D sector goes to landfill. So even though it's like just 10%, but then the number is quite high, it's about 5 million tons. So if you look into the waste hierarchy, so the first priority is to prevent the formation of waste, and followed by preparing to reuse. However, if the material cannot be reused, then the next option is to recycle. So recycling is nothing but any recovery activity by which the waste material are reprocessed into products, materials, or substances, whether for the same original purpose or for different purpose. However, energy recovery is not considered as a recycling. It comes under recovery. There are lots of legislations on waste management. I'm just talking about one particular legislation, which is on the landfill tax. So UK has the landfill tax from 1996, which has been growing. The price has been growing from 1996, and recently we pay about 102 pounds per ton for the waste that goes to landfill. In the landfill tax, I think it's categorized into two rates. One is the standard rate, which is applicable for most of the waste. However, we have a low rate landfill tax, which is much lower. It's just about 3.25%, but it's applicable for the materials which has very low environmental impact. For example, if you see, there are two pictures. The picture on the left side is the waste from a construction site. And when these wastes are formed, they pass it through the trommel machine. So trommel is nothing but just like a sieving. And the powder materials, which you can see, maybe it's not very clear. So these are the trommel fines, and they come under the low tax category because their environmental impact is much low because they're usually inert materials, and they're used in the landfill site to cover the waste in order to avoid the waste from flying. So these kind of wastes come under a low tax category, but there are lots of crimes happening around this low tax because people want to go to the lower tax category, so they kind of grind the materials and pass through the trommel, and they collect, and then they try to put it under the low tax category. So there are some new legislations like LOI, which is called as the Laws of Ignition Test, but I'm not going so detailed on it because that's not what I look at. So how the wastes are sorted and documented. So we use this European Waste Catalog coding system to document the waste. And so it's a 6-digit coding system where the first two is the chapter, and then we have in the middle is a subchapter followed by last 2 digits, which is specific to the kind of waste. So there are 20 chapters. Each, I think it's relates to the source of the waste formation, like the sector. For example, if you see, one is dedicated to waste formed from mining, and I'm particularly focused on Chapter 19, which is for the waste from waste treatment facilities. And Chapter 19 has subchapters, and in particular, I look into 1912, in particularly 1912, because it's the code that goes mostly into the landfill. So 1912, if you look into the description, it's the waste materials that comes from the mechanical treatment of waste. Other than those mentioned in 1912-11, 1912-11 is dedicated to, I think, hazardous waste. So 1912-12 is non-hazardous waste that mostly comes from the mechanical treatment. So mechanical treatment, for example, MRF site, where we send the mixed recyclates from the household, like the one at the bottom. So they go into the MRF site and they get sorted, and finally, whatever is not sorted or whichever doesn't fall into other categories, these kind of materials comes out as 1912, and they goes to landfill and incineration. And so when I talk about mechanical treatment, manual sorting of a material is also considered mechanical treatment. So there's lots of materials from construction site that directly comes into the landfill site, even without being processed through any treatment facility, because manual sorting is considered as the treatment, so they just directly come into the landfill site. So now I'm moving to the actual project. So the methodology I actually separate into two. The first one is to understand what are the waste that goes to landfill. I was provided a data sheet by DEFRA, which contains the quantity of different residual waste. So this data sheet just contains the non-municipal, non-major mineral waste. And to understand the nature of the waste, I visited and interviewed a landfill site manager at one of the landfill sites at Newcastle. So this is the data sheet provided by DEFRA. It had about 287 rows of different waste codes from all the chapters. And the total amount of non-municipal, non-major mineral waste is about 2.43 million tons. But if you look into the top 6 of the list, that total to up to 56% of the total waste. And the top two is the 19-12-12 from CED and Exeter, which is about 33%. So that's why I focus on this particular waste code to understand what's the origin of this waste code and what we can do with this waste. So I visited the landfill site and got a few pictures of the truck that just came from a demolition site. And if you look into the pictures, the waste is quite diverse, like it's not uniform. It also had some kind of soils and radiator. I'm not able to show the radiator in the picture. There was like few radiators, mattresses, carpets. So the main thing has to be done is the initial sorting of the material. That's what had to be done, and it was not done. And when I asked the landfill site manager, he mentioned that to pay a manual labor charge to sort these materials at the source is much more higher than the price that they would pay to landfill this waste. So these producers, they don't really sort the waste. They just dump it in the landfill site. So it has to be sorted at first. So this is just one idea that I propose. It's not from any article. So initially we have to sort out all these big waste like the polymers, like mattresses or carpets and big aggregates and everything. After sorting them, we can pass these waste to a thermal screening, and then we can collect the fines, and that can go as a landfill cover. And then we can separate the metals. Finally, we can separate the bio waste like wood chips, sawdust, and then lots of foams and plastic waste, textiles, and cardboards. So these are the 5 categories from the waste that I observed from the landfill site. So we can categorize into inert and metals and some pure biomass waste like the wooden logs and cardboards and papers. And there are some pure plastic waste. And I have given some examples on the table. And there are some waste which are like biomass polymer mixture. There are lots of technologies, like John mentioned. I'm not going in detail into the technologies. There are lots of different technologies that can be used, but I'm just pointing for important technologies or promising technologies for treating these waste. Anaerobic digestion, gasification, pyrolysis, and hydrothermal liquefaction. So because John showed a lot about these things, I'm just quickly moving. However, we have to consider that the construction wastes are mostly contaminated, like they are not fresh materials that can be recycled. So for the polymers, the first priority is obviously the mechanical recycling. But to some extent, mechanical recycling requires a pure polymer. So if they cannot be mechanically recycled, then we consider recycling by these chemical recycling technologies. In case of anaerobic digestion, it's suitable only for biomass. So any plastic contamination should be removed. So biomass can be treated by anaerobic digestion. It's an excellent option, and it can be treated by gasification. However, we have to make sure that the biomass has less ash and less moisture. So it can be also processed by pyrolysis and HTL. But pyrolysis, again, we have to make sure it has less moisture. It's not good for moisture content more than 10%. And HTL is a very good option because it happens in the presence of water. So the moisture content is not a problem. For the other polymers like PET, so for the polymers, AD is not a good option. But the other technologies, in case of pyrolysis works really good for polyethylene, polypropylene, and polystyrene. But HTL works good for all kind of plastics and also plastic biomass mixture. But what's the current status of these technologies in the UK? As I mentioned, AD is a well-established process, and we have a lot of units in the UK that process, about 702 AD units until 2022. And usually they process the food waste, crop residues, and slurries. And however, like I mentioned, AD is very sensitive to polymer contamination, so it's suitable only for biomass waste. In the case of gasification is also a well-established process, particularly for the fossil feedstocks. However, the gasification has to be followed by the catalytic conversion of the syngas, and this is still not, it's still in the TRL level of 5 to 6 in the UK. In the case of pyrolysis, again, we have lots of pyrolysis units in the UK, but they are mostly small plants, and they are not big plants. So Plastic Energy will have their first pyrolysis unit for treating the mixed plastic waste, but they can process only polyethylene, polypropylene, and polystyrene, and it's not suitable for other kind of plastic waste. However, hydrothermal liquefaction, it's mostly in the lab scale. And Mura will have their first first plant in Teesside, which can process all kind of plastic, including the difficult to recycle materials. So this is my last slide. So I have few recommendations. I just point out the main one. So obviously the behavioral changes is very important. The waste has to be sorted at source before it is brought to the landfill site. And we need a proper system for tracking and reporting the organic construction waste, and collaboration with the waste management companies to ensure that the organic waste is properly collected, transported, and processed. And we need more strict regulations and guidelines for how to handle the organic waste from C&D sector. And finally, we don't have enough large-scale projects, large-scale projects to conduct the economic feasibility analysis. So we need more research in this particular field. Thank you so much. I would like to acknowledge many people who helped me in this project. I had lots of meetings with DEFRA and Environment Agency, ESA, and Suez was very kind to give me a chance to interview the landfill site manager, and lots of people from RAP was giving me lots of input, so I would like to thank everybody, and also C-Hub and my center. Thank you.
Okay, in that case, I'd like to thank both three postdocs again. I think they've given much better kind of flavour than the general overview, so thank you very much. And I think this almost takes us to the end of the day, so Fiona, I guess you want to come up and finish us off.
Thank you to the CircularChem Centre for rounding off these last 3 days that have been absolutely packed full of exciting stories and insight and findings from the research of the NICER programme from across the 5 centres and the hub. The aim of the 3 days really was to showcase some of the research that's coming out of the NICER programme as we've reached just over the halfway point. And the hope was that each of the centres and the hub and the stakeholders and the partners that we're working with will learn more about that research and identify opportunities for more collaboration, more amplification, and working together towards those all-important cross-programme outcomes. And I've certainly learned a lot more about all of the research than you can read in a report. And I mean, one thing that's really been fantastic to see is the researchers behind that research. And I think it's been great to see the PhD students, the postdocs, as well as all of the investigators working on the programme. It's been really, really inspirational. Just really want to thank all of you for sticking with us to the end, but obviously all of the different people that have attended over the 3 days. Thank you to the University of Birmingham for hosting us in this beautiful building and an amazing campus. The weather has definitely helped, but also for looking after us so well. Thank you, obviously, to our funders, to UKRI, and all of our supporters, to DEFRA and to Department for Energy Security and Net Zero and other devolved administrations, and obviously all of our partners and stakeholders that have been showcased throughout the 3 days. Big thank you to the working group who have put the showcase together from all of the centres and the hub, and then a special thanks to Imogen and to Katie for all of your hard work in putting the 3 days together. So we have got, before you share a round of applause, we have got a video, and that will mark the end of the showcase. So I just wish you all a safe journey back and look forward to collaborating with you over the remaining 19 months. Thank you.
HEIs has coordinated the NICER programme, making great strides in achieving our goals of moving the UK to a circular economy. This midpoint is an excellent opportunity for us to take stock of our progress and to underline the importance of our collaborative efforts to embed circularity. We've initiated multiple mechanisms to support cross-programme interdisciplinarity and build capacity and capability amongst researchers, partners and the wider circular economy community. Collectively, we are conducting groundbreaking research to tackle technical, scientific, industry, behavioural and policy challenges in moving from linear to circular systems at scale. Exciting breakthroughs include circular metals electric pulse treatment, extending the service life of a steel component by 75%. Metfatech, construction minerals, and the CE Hub bringing together approaches for material flow and whole system value chain analysis. Circular Chemicals work establishing life cycle assessment methods for the UK chemical economy, and Textile Circularity Centre's environmental analysis of textile bio-waste processes. The NICER programme has also accelerated understanding of circularity across resource flows and sectors, building collaborative case studies, developing circular business models, and analysis of UK public data assets and policy levers, and cross-programme knowledge transfer events. But we don't intend to stop here. For the remainder of the programme, we are even more focused on cross-centre collaborations to cement NICER's legacy and, more importantly, demonstrate the system-level impact we set out to achieve. Despite the inevitable challenges that lie ahead, the progress made by the NICER programme is a testament to the dedication and ingenuity of those involved and inspires hope for a more circular future.